So yeah, first of all, welcome everyone, and thanks for joining us today. If you're thinking, wow, yet another webinar, why am I here? Is this yet another webinar, and that too on AI? Yeah, in fact, you're actually right. This is, yes, yet another webinar, and this is again on AI. So you'll have to hear us, but I guess we'll have something slightly different and unique in the sense that we'll have a bunch of young people talk about AI. It's not like people who've been in the industry, who've written books or who've got, or in the process of writing books. Srini, I'm letting out your secret there. We're not having people like that talk about AI today. We're getting people who are doing the work on the ground, who are actually implementing quite a few AI projects, and that too complex ones at that. We're letting those people talk and talk through their experiences as they go along, building whatever projects and implementations that they're doing. So that's the first part of it. Of course, this is going to be interesting in the context of what we're going to be touching today is not so much about how do you call it? Not so much about the sexy portion of the AI project, not about the deep end of AI where you're talking about what models, etc. That's also there, by the way. But what we're talking about and focusing on is the labeling or the annotation side. There's been a lot of interest in the world in general around AI. But there are a lot of things that we'll need to work towards improve and do it a lot more diligently before we start taking advantage of all the implementations that are out there. So, Ramya, if you could go to the next slide, please. I want to just take a minute and show you the faces of the people that are going to be running the presentation today. So we have Ramya. She is more like a tip of the spear for us. So she is the, for all practical purposes, the opening batsman. She goes in, talks to the client, figures out what they need, and then gets the team to do the hard work and essentially chills out after that. Dheeraj is our, you could call him our orchestrator. He's the guy who keeps things together, gets people to do different things, ties them together, and delivers the final project. He's been working on something very exciting within RoundSqr, and he's probably going to be talking a lot more in detail about what he's doing here. And then you've got the people that you are waiting for, waiting to hear from, that is Raju and Akhil. They are the data scientists in the company. Again, they've been doing a lot of interesting stuff, trying to get AI into annotation and labeling, which is not considered that very key in that sense. So yeah, those are the geeks on the team, Raju and Akhil. And where everybody else fails, there's always Srini to pick up. So Srini will do the closing statements and he'll leave us with what the future of AI is and how things are changing in that sense. So yeah, over to you guys. Ramya, take it away from here.
Thank you, Sirisha. So good evening, everybody. I think it's indeed a very exciting session. Even for me, the topic especially is very interesting. And the coronavirus that you see on the screen right now, it is not just to grab your attention. But then in a recent webinar like this, I got a question which is on basics of AI/ML. I got a question which says, if AI is so great and if we have data coming in from across the world, then why is the progress on this particular situation still slow? So that is a very interesting question because till day today, data is a problem. The world was facing a problem gathering the data, collecting the data. But now, thanks to advancements in technology, I don't think data is a problem right now. We have enough data available in the world. The hardware, the hardware is supporting enough to collect enough data. And even the computational power of the systems has increased so much that we are able to run even huge models effectively. But then what is the true bottleneck here? It is labeling the data. So even for that question that I got before, yeah, we get a lot of data in terms of the x-rays, the test reports, the scans and everything, but and in all different formats, but who is going to actually label them? Who is going to tell that this is a pneumonia one, it is a flu, it is a cold or cough, or actually coronavirus? So who is going to actually label it? This is going to be a very, very pressing question. And then if you look at a popular survey here, or analysis here, 80% of the entire time for an ML project goes in data gathering, uh, cleansing it, labeling it, and augmentation. So the actual part of the ML, where people are like running after ML, that is only 20%. The total time of the project, only 20% is allocated to ML, and rest of the 80% is on data. And then in that, around 25 to 40% of the time is completely going in labeling and augmentation. So 25% is purely on labeling. So it is a huge amount of time. I'll not bore you guys with stats anymore. Uh, so why is labeling very difficult? Why has labeling become a bottleneck in the times now? So it is a lot of time, because the huge amount of data that is coming in from various sources and various formats. So it is a huge, it takes enormous amounts of uh, time. The ML project should have budgets to get in right people to label it, and it's a huge manual effort.
Ramya, you've gone on mute somehow. Yeah.
Yeah. So it is enormous amounts of time, money, and effort. So let's for instance think that a company has all the three. Even then, we have some other problems like this: ambiguity. So how do we label this picture? Is this Hulk, or is this Iron Man, or is it both, or should we label it Hulk in Iron Man suit? See, once we label it, even the outcome is not, either the outcome is not valid or practically not viable, like you see in the picture. So essentially what happens, even something which gets labeled may not be of high quality. So first of all, we have a problem of labeling it, and then we have the ambiguity there in the labels that the data scientists receive. And the next problem that we have is with the hierarchy and context in data labeling. So if you look at this picture, it is pretty clear. The lemon and orange have their individual names. So it's a lemon and an orange, but they are also fruits, and they're also falling under the category of something which gives us vitamin C. So the context is very important here. So are we talking about um, uh, getting the labels as names of the fruits, or are we categorizing them as fruits and vegetables, or are we categorizing them as for their character, for their properties of giving vitamin C, or something else? So the context here is very important. And uh, the quality of the, so what happens with the problems with context is, let's say we get a labeled data set, and then we start the project, and then the data scientists start to work with the data, but then they understand that the context has completely gone different. So even a data set which is completely labeled goes useless here. So that is the problem with this. So essentially, what causes problems in hierarchy and context is because of lack of collaboration between different teams. So there is an SME there who will be the subject matter expert who is actually helping out in putting right labels, and an annotator who actually puts the labels, a manager who takes care of business needs, and a data scientist who actually builds the ML model. So there is basically a loss of information from each of the units here. So just imagine if taking a Hulk example, or the pictures are just to increase your curiosity. But then imagine the scenario happening in a traditional large enterprise, or especially in healthcare, where there is data coming in terms of x-rays, scans, or the test reports, where each scan should be looked in and marked or labeled to the smallest structure available on the data, on the images, or on the reports that are received. And then not just one expert would be enough there. We would need multiple people to do the same thing over and over again, so that the correctness of the labels is ensured. So with all of these constraints here, and um, with multiple problems on multiple levels with data labeling, what essentially is happening is what we do is not in sync with what we build, is not in sync with the business needs. So there is complete, with just one process of data labeling in the entire ML project, there is complete fallout of the entire structure. So in the last 1.5 years of RoundSqr, we have been working on different vision-based problems, mainly in manufacturing and in healthcare. And I mean, we are no different. We faced all of these problems, and we still do have them on a daily basis, working on ground. So I'll now give this floor to Dheeraj, who is working on a similar project on vision based, and he along with the other data centers, as Sirisha mentioned, were attempting to solve this problem using certain technologies. Over to you, Dheeraj.
Sorry, before Dheeraj comes in, just a few ground rules for the team that is listening in. You don't have to be that very quiet. While people hand over from one person speaker to another, you could, if there's any questions, please go ahead and ask us. You're always welcome to put those questions on the chat window, and one of us will take it up and answer them as we go along. Yeah, if there's anything else, just message us, and we're just monitoring that, looking at it. Dheeraj, over to you, please.
Thank you, Ramya. Hi, everybody. Hope I'm audible.
Yes, you are.
Yeah, thank you. So yes, paying heed to the problems or the challenges or the bottlenecks faced by a typical enterprise, I will try and cover an approach on a technological standpoint in the coming few slides. So, Ramya, if you could just move to the next slide. So essentially, the way out of this problems that she's mentioned is I've laid them down into 5 points. I want you to think of this in an enterprise perspective. So it'll come down to the first point being managing and supervising operations of a machine learning project. So now this becomes important because at a top level, the manager will wish to see the progress, the status, and the overview of the entire cycle of work that is happening within an experiment or a project. And this is enabled by a common platform that we'll be providing to the different roles existing in the machine learning process. So this will avoid data discrepancies. In fact, will enhance productivity and assure a little bit of uniformity as well. And importantly, this has been always a case traditionally that once we start working with the data and the models, we lose track of which of those models belong to which of those data sets. So now that becomes a very important point, because when analyzing the performance, this becomes a key thing in data analysis. So versioning is very, very crucial. And coming to the fourth point, it is the core of what we are trying to do actually, to remove this bottleneck, so-called bottleneck of data labeling, through this powerful concept called active learning, which will make the process faster to solve this mountainous data annotation task. And on an enterprise level, you will always wish to have solid and standard performance metrics. And we have also found out some interesting ways to enhance the interpretability of the data labeling and your model performances. So through these couple of concepts that my fellow data scientists will cover. So yeah, so we at RoundSqr, Rami, if you could just move to the next slide. Thank you. So what we at RoundSqr have done is created a internal system, or a tool you can say, called Zastra, that aims at providing a prospective enterprise grade solution. Now I will carry forward by trying to explain how we went about that, by choosing what we have and why we have chosen that. So since you can actually, it's pretty evident that it's a cross-domain application, which will require multiple programming stacks, for which we have chosen the microservice architecture, right? So we use the Dockers for this microservice architecture. For those of you who are new, this is essentially you can understand that it is a platform, or you can say a concept where you can run your software dependencies associated with the program in one container and make it independent of the host. So the advantages of this are, you can have multiple programming stacks, like multiple languages, frameworks, or databases, and yet have a communication between these, because these are very well enabled to communicate with each other, even though they're loosely coupled, right? So in coming to the languages we are using one of the most latest programming languages developed by Google, called the Golang, for the backend processes, which is turning out to be comparable to the performances of C and C++. And coming to the UI, we've used AngularJS, which is also I'm sure familiar to all of you in the front end angle. And obviously the core of it sits with the ML frameworks, which is PyTorch and TensorFlow. TensorFlow again is there's a huge community behind this, backed by Google. So this tool has the following key features, which I will explain to you. Ramya, if you could move to the next slide. Thank you. Yes. So what we have achieved so far, and the current status of this is, we have successfully integrated the both the frameworks with several algorithms available for you to play with, along with enabling a range of hyperparameters for you to run your active learning algorithms. So this was a task in itself, and we have the complete workflow available for supervised classification and detection experiments. Now, what do I exactly mean by this? I mean that you can actually gather your data either from your cloud storage or your host system, get it onto your tool, and you can create projects, create experiments, and you can label them. You have an inbuilt annotation tool in it, and you can actually complete your work and finally export it as well. So this can fit into your enterprise pipeline, essentially. That is what we're aiming at. And we've created a collaborative environment, which proved to be a very big bottleneck, like Ramya had earlier mentioned. By creating multiple user privileges for a super admin of the tool, a manager, a data scientist, and an annotator. So it will go like the manager can assign tasks to the annotator, whereas the data scientist will have his own privilege to work on the data and create these active learning experiments, and so on. And we have also included features like integrating your web application with your cloud storage. So we have done this for Amazon's S3 for now, and you can also you can export your generated models to the your host or your cloud storage. And finally, we have also achieved we managed to achieve the topological data analysis for featureization of high dimensional complex data and explainability. This from here on, I will pass it on to my fellow data scientists, Raju and Akhil, which is the heart of Zastra, like the arc reactor of Iron Man suit. And this should be a very, very interesting talk. Thank you.
Thank you, Dheeraj. Thank you so much.
No, this Srinivas here. Just a small pause. I think there are a couple of questions. Let's try and get to them. Yeah.
Right.
Okay. First, let us kind of talk about Lavasesha. It's a classification is also done for text. Yes, it's not just for images. It's for text too. Then we have somebody, Sindhu Varuni. I am learning and practicing on AI by myself since a year. As Ramya told, 80% will be gathering data and labeling them, and the remaining will be done by a data scientist. So do you think fresh learners should actually start by going to source and collecting the data and preparing it? Or is it just enough if we learn how to build models using different algorithms to survive into a company like you to work? Okay. Should I take this, or will you take this, Sirisha, Ramya?
I will start and you can chip in, Srini. So,
sure.
So Sindhu, first of all, thanks for the question. I guess everybody who's starting off an AI and that to someone who's just about starting and learning probably are typically stuck there. A generic answer to that would be learning one portion of anything is not going to be enough any which way. It is not like you can figure out and learn how to build models and somebody else will do some other work. Doesn't get done that way. The world is changing really, really fast. In that sense, yes, you don't have to really literally go and gather data in that sense, but you should be what we call a data analyst, right? You should be able to look at the data, profile it, query it, massage it, change it appropriately, etc. You should have that skill set, and then use that as an input for building whatever models that you build, and eventually have the capability to, kind of expose those inferences as well. So net, what we're saying is you should be a software programmer come data scientist. You can't be one of the two in that sense. So what does it take to get into a company like RoundSqr to work? Being a software programmer in that sense.
Yeah, absolutely. So
Lavasesha sorry, go ahead.
Lavasesha, question for, okay, it's for me explicitly. So okay.
It's very, very specific. Yeah.
Can we also think a CNN or an autoencoder built with CNN as lens, as this flattening of the pixels, lose the spatial information? Okay. Yes, there is. Yes, you can. But the thing to remember is you're trying to. The lens will be based on spatial proximity, right? So the long distance spatial value will be lost, but the proximity will be enhanced. So yes, you can think about it like that. So that's what CNNs do. Essentially get you enhance the spatial proximity scores. And that's why they work well for images, fundamentally. Make sense?
Yes, sir.
Yeah.
Thanks.
Let's look at the rest of the questions post Raju's
Yeah.
session. Yeah, Raju, you take it off.
Yeah. Thanks, Risha. Yeah. So today we'll be going to discuss about the active learning for the scalable active learning for image classification. Ramya, can you go to the next slide? Yeah. So here it is a conventional ML pipeline. So generally what we do when we want to train an ML model. So we gather the data, we ask annotators to label all the images. If it is a domain specific, that we need to ask the SME review for the data. If everything is correct, we will train our ML model and get output. So in the passive supervised learning, not all images or data points in the label dataset have the same amount of information, which means whatever the images that you have from the unlabeled pool of unlabeled dataset, you might that all the images might not consist of the same relevant information. So we can choose the specific images or data points that are more informative using active learning techniques. So if you can go to the next slide. So in this active learning approach, instead of choosing randomly selected data points or images to annotate, we ask human experts to selectively label some items in the dataset. But unnecessarily annotating the whole dataset, here the algorithm iteratively selects the most informative images based on some value metrics or some criteria, so that these images will be sent to the annotator and who returns the true labels of those queried images back to the algorithm. So with this approach, model achieves a certain level of accuracy with less number of labeled instances. So if you let's take a look at the picture. So this is the process how we select the informative images by the learner and labels them. So the first step is human annotator chooses randomly selected images and labels them. And the next step will be we consider this subset of labeled images as training data. This training data will be fed to ML model, which is a classification model in our case. And then we take this small model and run inference through the remaining unlabeled data from the pool of unlabeled labeled instances, and we'll get the predictions from there. And after that, we will have an active learning query method here, which means we have a number of query methods we will be discussing in the coming slides. So with this active learning framework, we will get more informative images. Those unlabeled informative images will be sent to the annotator, and then the annotator annotates the images, and those labeled images will be added to the training dataset. And again, we have a new set of training data. This will again feed to the model. This is an iterative process. So for example, if you're initially starting with 1,000 images, so that is being fed to the ML model, and you'll be getting an inference from the unlabeled pool of the data set. And from there, you can select the most informative images and then ask to annotator to label those images. And when you have ready with a new set of images, so you will be training it over and over again, which is an iterative process. If you can look at the learning curve, so basically the learning curve is about getting better learning curve. So what you see in the graph, you see over there, is basically like showing the y-axis. Y-axis the show accuracy or the quality of the model, and the x-axis shows the amount of labeled data. So what you see in gray is what you will have if you give more data randomly, like an incremental supervised learning. So you are incrementally adding more and more data, but there is no intelligence way in the way, but you decide to add. So each one of those examples or the samples that you add incrementally are going to be randomly selected. Of course, it goes up because we all know that the more data, the more there are, higher you get the accuracy. But this statement is not is valid up to a certain level, which means after adding more and more data, the model gets complexer at certain point, and then it will get distracted from the get deviated from the optimal value. So active learning is about like allowing the model to learn faster. So now if you have an option of deciding what data you want to put into the system, and you know which one is going to be the most beneficial of your model, then you can have the model learn faster and reach higher accuracy even at a faster rate, right? So you can see the dotted blue lines are there. So with the passive learning model reaching around 80% accuracy with the 80% of the label data. But in the case of active learning, you are getting the same almost 80% of accuracy with around 50% of the data. So before talking about how active learning works, we should know some basic principles of active learning. Empirical risk minimization. So the concept of empirical risk minimization becomes relevant in the world of supervised learning. The actual goal of supervised learning is to find a model or hypothesis that best fits the given data set. Here I'll be using a model or a hypothesis interchangeably, which means the same model or hypothesis, both are same. So please don't get confused. We actually want to find the hypothesis that minimizes our error, right? So with this, we come to the term empirical risk minimization. The core idea is that we cannot know exactly how well an algorithm will work in practice, which is a true risk. So because we don't know the true distribution of that data algorithm will work on, so but can instead measure the performance of a known set of a training data, which is empirical risk. Or let me put in this way. So in general, the risk cannot be computed because the distribution, the true distribution will be unknown to the learning algorithm. So however, we can compute an approximation, which is called empirical risk, by averaging the loss function on the training set. Since we have only access to the sample space, so we learn based on the sample of training examples. We don't have access to the true error, but to the empirical error, which is also called a generalization error. So basically, the empirical risk minimization principle states that the learning algorithm should choose a hypothesis which minimizes the empirical risk. Now we know the ARM algorithm is one that selects the solution from a hypothesis set in such a way to minimize the empirical error on a training set. So the same you can observe in the graph. So if you can observe the red line, which is coming to the optimal value, whereas the blue dotted line is getting deviated from the optimal value. The point where it gets deviated is the expected risk that we are about to consider. So now VC theory, or Rami, can you say? Yeah. So VC theory or Vapnin-Chervonenkis theory. So according to this theory, for an ERM binary classification, for any target function and an input distribution, any
yeah, I think Raju, you can just, there's actually a question, okay?
Yeah.
So let's kind of see what the question is. Sorry for distracting you, but
yeah, no problem.
How do we, it's from Kaushik, and the question is, how do we define the data input threshold to the ML model as more and more inputs will distract the accuracy? Yeah, I'm not 100% sure if I understood the question, Kaushik. Can you tell me what you mean by that? So what happens? Why do you think as more and more inputs will distract the accuracy? What does that mean? Sorry.
Yeah, while we wait for Kaushik,
Okay.
Srini, I think it's basically something to do with what Raju was mentioning, right? So not always more data is going to make your model better. It is the validity of the data that goes in, the right kind of data that needs to be fed into the system.
Oh, okay,
otherwise,
okay,
that's the context. Yeah.
Oh, okay, fantastic. So how do you define the input threshold? For classical statistical learning, I think he's just going to touch upon this. VC theory gives you a statistical bound for the number of samples you need for a given accuracy. So when you're dealing, and I'll let Raju explain that. Yeah, hopefully that will make sense for you, Kaushik, and thanks for the question.
Mr. Srini, can I continue with my flow, or else I answer his question and then?
No. Please, I think if you continue, that will be answered, I guess. Go on.
Yeah. So basically, where should I stop? VC theory, right?
VC theory, yeah.
Yeah, according to VC theory, for an ERM or empirical risk minimization binary classification, for any target function and input distribution or any hypothesis space H, the VC dimension and the N training examples, the algorithm is consistent and will produce a training error that is at most from the true distribution or true error. So, and if you aren't familiar with VC theory, you can just think about D as a dimension of your feature space. That would what it would be in the case of a linear classifier. Basically, VC theory establishes a relationship between generalization of a learning algorithm and properties of a hypothesis space H of a function being learned. So the best approach for selecting the hypothesis from hypothesis space H, which is closer to true distribution, is a disagreement-based active learning. Now, coming to disagreement-based active learning, it is generally used in streaming model where unlabeled data points arrive one at a time, and for each, the learner has to decide on the spot whether or not to ask for its label. When I say it is used for the streaming model, it doesn't mean that it is not used for a batch model. Of course, it will be used, but the most commonly used it in streaming model. So in the case of linear classifier, so what we are going to do here is consider a point or unlabeled example in a figure A. So we can clearly say that unlabeled example belongs to the negative class. So in the figure B, we are going to focus on linear classifiers that separates the positive and negative classes. So that's what one of the classifiers look like. We don't know which one it is. So it could be in any orientation zone. So what we are going to do now? So we are going to follow this empirical risk minimization idea. We are going to take a bunch of examples that draw them at random from our pool of unlabeled cases. Ask our human expert to label them and say we get these negative and positive classes. So now what does that mean? It means that we know that the only linear classifiers that could be consistent with these labeled examples are the ones I have shown here. Okay, all the others we can rule out, and because they would start to misclassify things. So what we are going to do then is when to focus now on this region where new examples might distinguish between those remaining hypotheses. This is the region of disagreement. So we are now going to look at it. The mission will go and look at the large set of unlabeled examples remaining in the data set, but it's not going to label all of them. It's only going to label ones that in a pink region, which is a disagreement region. So it's going to say, forget about all those, just label those two and update your hypothesis. So we improve it rather than having a labeling a bunch of examples. So we focused our sampling and only label two here. So that's the idea of disagreement-based learning. So this is what disagreement-based active learning is. So that the challenge with this approach is, in the deep learning world, it doesn't hold the VC theory bounds, which is the VC theory bounds tells us that, states that the number of dimensions should be less than the number of samples. So whereas in the deep learning world, the number of dimensions will be greater than the number of samples. Even that's the reason that we don't use this, we don't implement this in the deep learning world, since we usually deal with cognitive data which is high dimensional. And the second reason is it is intractable and computationally expensive. And that's the reason we have chosen uncertainty based active learning strategies in the deep learning. And yeah, so the next uncertainty based active learning strategies will be shared by Mr. Akhil. Thanks.
Thank you, Rajan. To avoid, next slide, Ramya. Yeah, to avoid problems in traditional active learning method that are raised by Raju, we have selected uncertainty sampling framework. It is a simplest and most commonly used query framework in the active learning area. Here, the idea is to select samples that are the model is most uncertain about. Let me give you an example. If you look at the first plot on the slide, we have a two-dimensional space with positives and negatives of 400 examples coming from two different Gaussian distributions. If you build a classifier with a random examples, you might end up with the 70% of accuracy with a given label data set. And here you can note that it is also taking the points which are far away from the classifier. If you look at the third plot on the slide, if you use uncertainty based sampling method, you will get this type of label data sets and classifier. So this method did not consider that the data points that are far away from the classifier, which are not informative, because all these actions are happening in the middle of space, and you got 90% of accuracy with the same number of labeled data set. So this approach straightforward for probabilistic models. For example, when you are using probabilistic model for a binary classification, uncertainty sample and simply queries the sample whose confidence score near to the 0.5 or near to the 0.5. Yeah, in the next. So we have bunch of query methods available, but these are the most commonly used query methods in the uncertainty sample. So first one is least confidence, and second one is marginal sampling, and third one is entropy based uncertainty sampling. In this method, in the least confidence method, classifier selects the sample which has least confidence. If you can see the formula, 1 minus probability of y given x. Here theta indicates the hypothesis or model. So and it is most probable label value. But the least confidence strategy only considers information about the most probable label, so it efficiently throws away information about the all other label distributions. It is not really considering remaining label distributions. To avoid this problem, we are taking marginal sampling query method. So in the marginal sampling query method, it selects the samples that have smallest difference between first and second most probable labels. So it corrects the flaw in the least confidence strategy by incorporating the second most likely label. When you we use only most probable label in the LC method, but we are including second most probability also value also, as you can see in the formula. First one is first probable label value, and second one is probability of second probable value. What formula says the difference between first most probable label and the second most probable label is equals to basically is equals to marginal sampling. So if the difference between two mostly likely probabilities is low, then the model has little doubt on a particular sampling. So if the difference is small, then the sample is unclear. So we can ask Oracle or annotator to ask to do the labels. So here we have a problem with this method too. It still ignores the output distribution for remaining classes when we are dealing with large set of label data. So and And if you take binary classification, these three methods give the same results. In the entropy, next slide. So I'm going to explain entropy-based uncertainty sample, which is using in R2, JASTA 2. So entropy is a measure of uncertainty or information nets of a random variable or distribution. Here we are using Shannon entropy. The base concept is taken from thermodynamics or physics. Let me explain you entropy formula. So here P is the probabilities of the events, and base of the logarithm is 2 in the Shannon entropy. If you consider, if you take entropy in the physics or thermodynamics, the base value would be Euler constant, which is proportionality constant. It gives proportionality constant, and H is the measure of uncertainty given probability function. And if you get a higher value of H, it basically tells that the sample is more uncertain. So for example, let's take an unbiased coin. It has high entropy value because you have chances to getting heads or tails. It has a lot of information that you don't know about it. In the case of biased coin, it has a low entropy because you always get heads only. There is no other information. There is no other information it carries. It doesn't tell you anything new. If you take biased coin, in the slide you can see entropy values for a fair coin and unbiased coin is 1 and 0 respectively. So how we can interpret 0 and 1 entropy value? So imagine that you have a communication channel between you and your friend. You have to tell your friend what is the outcome of coin flip. So in the case of fair coin, you will always need to tell one bit of information about the outcome of the coin flip, whether it's or tails. In the case of unfair, you need not to tell anything about it because it always gives you the same. Your friend always know outcome would be heads. So there is no other information you need to tell to your friend. And the entropy value will be greater than 1 when you have possible outcomes more than 2. In the same way, consider class of predictions as outcomes. We can measure Shannon entropy of a predicted class probabilities. Higher value of entropy indicates greater uncertainty of a probability distribution. So in each active learning step, we calculate the entropy or the predicted class probabilities and select the example with our highest entropy, and we ask annotator or Oracle to label the example. So it is a iterative process. We should have some criteria to stop the iterative process. The next slide. So yeah, in the active learning area, stopping criteria is unclear. There is no definite process to stop the active learning iteration. It really depends upon what context you are in. So if you need model in the next second, you can stop. If you need model in the next second, you can stop active learning iteration and evaluate the model, and you can use it. It holds the information from the previous active learning iteration. In some companies or some enterprises will have limit on labeling budget. If you can afford only certain number of labels, it will just run up until your budget limit exceeds. You will get guarantee on your model in terms of what label budget is. So you can stop when you exceed your budget, when you exceed your budget. And another criteria for stopping active learning iteration, when you run out of unlabeled data sets. Assume you have a small amount of unlabeled data. On each round, it is using some number of unlabeled samples. There is no point in running another round of active learning iteration when you run out of the unlabeled sets. And another way to stop the criteria is to check your error rate or accuracy. And another, it is an iterative process. You can evaluate the model after each iteration, and you can look for accuracy or error rate, what you are aiming for. In this model, if your model reaches your desired output, you can stop active learning iteration, and you can proceed for deployment or anything. So, and we have a couple of challenges with active learning. In the next, I'm going to explain it. Okay. Yeah. So, first one is representativeness of training set in the active learning evaluation. Here we are trying to reduce the number of instances to get decent accuracy. So if you want to evaluate your model with a number of instances using a cross-validation method, you might the value might be questionable. You cannot rely on this value because you're using only small set of labeled data sets. So in the real world situation, you need much larger evaluation sets to achieve the proper value. When you're trying to examine the classifier performance, it is trained on the difficult samples or informative samples. So that the accuracy derived by the internal cross-validation method strongly underestimate the true distribution, true classifier performance, as we are not considering less amount of data. And the second and most important one is sampling bias.
Yeah, I think maybe Akhil had some trouble with his audio. Let me actually quickly step in, probably, and just very quickly talk about what Raju and Akhil talked about. I'll take 10 seconds. That's all. So essentially, the gist of Raju's small discussion was the fact that a lot of statistical learning-based VC theory does not work in the deep learning era, because your number of dimensions are nearly equal to the number of samples, right? So we will have to figure out a newer way of doing it. And that is the whole uncertainty-based methods, where you are fixing the model, you are fixing the hypothesis and trying to understand the best value of parameters for the data. So that's essentially what it is. And on the other side, what Akhil explained was actually very important. So he was trying to explain uncertainty-based active learning using entropy. See, the only thing you need to understand about entropy, guys, is entropy is a measure of surprise, okay? So when entropy is high, it fundamentally means the world is full of surprises. So it's a lot of disorder out there, right? Because when you don't know anything about anything, you will think all outcomes are equally likely, right? And when you know something about something, you can kind of try and narrow it down. So that's the entropy bit. And the other thing, I think, where I think he probably lost a bit of his audio was there are two problems, right, with any active learning approach. The distribution of the data is different from the original distribution, because originally you're given an unlabeled set of data. Now you are training this model only on a sample out of that unlabeled data set using whatever, but that still changes the distribution. So it induces a sampling bias. How do you get rid of it is the big open question within all of active learning. Hopefully that makes some sense. Okay. I saw a question from Kranti and I saw a question from Malini, which I think, which is how financial industries can embrace image analytics. There are a lot of ways. One of the obvious ways that at least I have worked with financial industries is around know your customer type problems. So that whole, there's a whole part of financial industries that deal with know your customer type problems, and there they do embrace a lot of image analytics, right? A lot of facial recognition, a lot of even other types of video feeds they actually use in order to do that. So that, yeah, I see a thing from Siddharth. Shebyshev's inequality is another matter. For example, yes, Shebyshev's inequality. Definitely, when of course there are constraints around when and how you want to use Shebyshev's inequality, but central limit theorem, if it is IID Gaussian, and yes, in which case Shebyshev's inequality can be used. VC theory is just a more generic statistical learning based method to do that. But I have nothing against Shebyshev or Chenkov or all of those inequalities also work, provided those assumptions hold. That's all. Thanks for the question, Siddharth, and thanks for the question, Kranti. Feel free. So it doesn't, if it is something about this talk, it's okay. Even if it is something else regarding generally ML that something was bothering you for a while, you can throw it at us, we will try.
So Srini, I had a question. So how relevant is this supervised labeling going to be? So I keep hearing the stories around everything can be done by the machine. We don't need human intervention at that level anymore. So what's the future? Is there supervised learning at all that is going to continue to be relevant?
Yes. For the foreseeable future, it's going to be all supervised learning. Because the point is this, we all get excited by some reports that Google or Facebook publishes, but most of them are not ready for enterprise adoption yet. In the sense, we are not ready to act, because fundamentally you got to be able to underwrite risk. And we are not able to underwrite risk for a lot of those newer approaches. We're still trying them out. Supervised learning is still the only approach that has a decent theoretical backing for us to be able to kind of do any. Okay, so yes, for the foreseeable future, I don't see in my working life supervised learning going away. Hopefully it helps. Okay. What are the applications of Santosh Kumar? What are the applications of active learning in daily life? Anybody wants to take a stab?
Yeah, this should be a question for the audience for having listened to the talk so far.
Yeah, somebody wants to take a stab at it. Why did we sit in this place for the last hour and more than an hour, I guess now? Okay, I see Siddharth again. The more quintessential problem. Yeah, but we'll get to you, Siddharth. Thanks for the question. First, let's try and answer Santosh's question. So if nobody is going to attempt it, I'm going to attempt it. Applications of active learning in daily life. I think it's not really about daily life, honestly. You and I are not going to use active learning to kind of live our daily life. But in supervised learning, of course, the goal is to achieve the required accuracy with lesser and lesser labeling, because labeling costs time and money. So active learning lets you do that, right? Active learning lets you get there faster and hopefully cheaper. And if you do it right, you can actually write models that actually generalize better too than passive learning approaches. But that's for another day. That's not guaranteed by any stretch of the imagination, but it's possible. Hopefully, did that help, Santosh?
Yeah. So in the context of daily life, I guess it's more to do with if you use active learning to, fast track and do a much more accurate way of labeling data, whether it is in the healthcare spectrum or the KYC example that Srini was talking about. Maybe our Aadhaar card photos will be easy to understand and represent us better. Maybe if somebody scans your Aadhaar card, they will actually be able to remember your face and figure that out. So yeah, there's a lot of stuff that will happen in the context of using active learning in that sense to make things faster and better and cheaper, hopefully. Yeah, that's I guess the bigger context there.
Yeah, from Siddharth, apart from labeling, the more quintessential problem we faced during our project is to gather the actual images in a controlled environment. Is there a methodology in RoundSqr to mine images? Yeah, absolutely, Siddharth. A very, very valid question. Okay, and I have grappled with this for over 2 decades now. So yes, it is a problem. But there are 2 sides to this problem, right? One is getting the right images themselves and getting the right images in a controlled environment. That's another kind of a whole different problem. So the way you have to do this and the way it actually works is, if you are working on a vision project, please understand that light is your best friend and worst enemy. So you will always have to make sure of all the other features of an image, like its orientation and shape and size and whatever. The most important is light. Okay, and you will always have to clearly baseline the lighting conditions required for your project. Okay, it has to be clearly known, and the data that you gather has to be in line with it. Otherwise, it will be a problem. Okay, so how do you do that? The approach that we have is generally, at least I and my team, especially Raju or Akhil or the other data scientists in the team, they come up with a set of parameters that are important for solving this class of problems. For example, if you're trying to do some sort of classification on metal, then there is a lot of light reflection that goes on. So you definitely need white light, and you need white light at angles as close to 90 as possible, right? If you take images with 30 degrees white light on metal, and if you're trying to do defect detection on it, it's not going to work. I don't care how great an algorithm you're going to have, it's not going to work, because there's going to be so much patches of reflection on that surface that you will never be able to see anything on. So it's not an easy problem. The only way you solve about it is write those conditions clearly, and hopefully you have an educated and well-meaning customer who understands it and is willing to walk with you on that. Okay, there is no easy way to do this. Okay, did that help, Siddharth? I'm assuming it helped. Okay.
And people can feel free to talk as well.
Yeah.
Not mandatory that you have to type.
Yeah. This is not. Yeah, actually, this is looking very formal for me. I'm usually not this formal, so you can. We've got once more with Sindhu. Thanks again. So, generally, we have been trying to introduce fraud detection for a blank client using ML in the current company. I mean, there are a lot of banks and frauds in India. Are they already using AI? They all say they do. At least they all use machine learning for sure. Most of them do. Okay, to be very honest. Fraud detection and anti-money laundering is one of the oldest use cases for ML, back from 60s and 70s, honestly. But are they able to perform at a level the banks need them to? The answer is no. Okay, there are too many false positives, and that's a huge cost. And how can we do that? Is probably a consulting engagement, Sindhu. So we can talk about it, but false positives is a big problem.
And Srini, in the in the context of what Sindhu is saying, and if you put that in the context of what we are talking about in the image analytics space, there is the existing models that are pre-trained and all of that are not so much on the Indian in the Indian context. And can you talk
Yes.
us through that part of the story a bit?
Yeah, that's true too. That's true too. Most of them have been, I guess, because what happens is they use these anti-money laundering or fraud detection off-the-shelf products, like whether you're talking about in SaaS or SPSS or there are many, many more AML products out there. So these have typically been trained on very, very Western data sets, and they typically do not scale or do not perform as well, because the type of fraud that happens in Indian context, I presume, is very different from the type of fraud that happens in a Western context. So yes, that's a big problem, and a lot of people, and especially when you buy these black box models, they don't let you fine tune, right? They kind of give you the model, and you're supposed to use it and trust it as God's gospel. So that's a big problem. Okay, and we can talk about it, Sindhu. There are a lot of approaches that are coming up now, more in terms of anomaly detection rather than classification and all of those sort of things. We can talk about. Okay.
Srini, your favorite topic of topology?
Oh, okay. Is there a question there? How topology is associated with active learning? Yeah, this is a whole webinar in its own. So I'm not going to get into the entire detail. The key idea is this, right? So when you do active learning, what's your biggest problem? Your biggest problem is your sampling bias. Sampling bias is your biggest problem, right? You can all do the empirical risk minimization, but how do you know that you're actually catching hold of the expected or the expected error, which is the true error rate? There are no guarantees. So what approaches like the mapper algorithm in topology let you do is understand the different types of failures your active learning model is making. So for example, your active learning model can make a wrong prediction with a high confidence and a right prediction with a low confidence. What would you want to do? Ideally, you would want to increase its confidence of its right prediction and decrease the confidence of its wrong prediction. So how do you do that? For you to be able to do that, you kind of need to understand how these errors are distributed in your data, and then to try and cluster them together. So something like a mapper algorithm from topology lets you do it. And one of the reasons why mapper works is because it's deformation invariant. But like I said, that's for another day. I hope it's given you the high level discussion on this. We can get into details. Maybe you can email me or something, and then we can talk about it in detail. Yeah, I see a question from Malini. We are basically using heuristics and active learning for handling selection. Can we instead replace these kind of heuristics with some kind of meta learning? Yeah, that's a valid observation, Malini. That's a valid. So you're talking about some like a single shot or a few shot learning type or meta learning approaches. Can we use that to kind of handle? The whole problem is it's still a circular problem, right? Because you still need to prime them. You still need to have the pre-task model that will actually work on these downstream tasks and things like that. Yes, people are trying, but again, it's the same thing, right? It's a circular problem. If you could solve it, then you could have solved it already. But it's still an approach that we can talk about. Okay.
And Srini, maybe that's the segue to your closing statements also. I know you wanted to touch upon single shot learning.
Yes, that's a good idea. We'll just, I think it's we're getting close to time. So yeah, let's move on. I'll quickly try and go through my slides. Yeah, I think closing remarks. Yeah, fine. Yeah, let's go. So the first slide I want to talk about was a little bit, right? Everybody here has seen this diagram, I presume. It's very simple, right? The training error goes down, the test error goes down, and there comes a certain point where the training error goes down, but the test error goes up. That's what Raju was talking about, right? Empirical risk minimization. So at some point, minimizing the empirical risk does not pay off. right? This is how we were all taught. This was what was taught when you were trying to, but deep neural networks seem to throw this out of the discussion, right? Because deep neural networks seem to be able to kind of reduce the empirical risk to nearly zero, but they still seem to generalize very, very well on the test data. Doesn't make sense. In statistical learning theory, this does not make sense. It should not happen, but it happens. And it's been confounding a lot of us who work in deep learning for a very, very long time now. So, so hopefully this was a good piece of information to understand why disagreement-based learnings or why VC theory do not work in the world of deep learning, because all of them assume this particular, they kind of assume this way of error working, which the error in deep neural nets does not work. Okay, so moving on. So yeah, so what did we do? As mathematicians and physicists, it's like that Sherlock Holmes things, right? If you throw the impossible out, whatever remains, however improbable, must be true. So when certain things happen and we can't explain it, the only way to kind of explain it is make it a double descent, right? Because that's the only way we can explain how neural networks are able to reduce the training error but still generalize well on test data. So we would assume, or we think right now, there is no theoretical, there are a lot of practical explanations for this. There's still no theoretical foundation for this sort of an assumption, but this is what a lot of scientists agree now. So the idea is in the neural network domain, we actually have this double descent, where after a certain point, the test error again starts going down, even though as the training error tends to zero. The only problem there is, if you could do this infinitely, you might ask me, I could keep doing this infinitely. I can get this red graph to 0, 2, which is essentially what we want. We want zero error on the test data. The only thing out there is the x-axis, the model complexity. So the model complexity increases, and it increases non-linearly. Actually, it's not kind of shown here, but after a point, it's a non-linear increase. So if you have seen models like GPT-3, you might have heard of it, right? The NLP GPT-3 model, more than 1 billion parameters, pretty much has revolutionized all downstream NLP tasks. This is what they're doing. They've increased the number of parameters close to 1 billion. It costs about 20 million to train. So $20 million to train. I don't know. It's probably more carbon emissions than a few villages in this country. So extremely, not very efficient. But theoretically, you can do this, right? So that's why you got to think about it in terms of Occam's razor, right? So this far and no further. So how far does it make sense, and where you shouldn't go? And that's the whole game today in deep learning, right? There are people who are saying we go more and more complex, deeper and deeper, and kind of do this the brute force method. There are also people on the other side who are thinking we may have to think about this in another way. This x-axis does not seem very right. So hopefully that kind of gives you an idea of where we are. And so when we're talking about active learning, we need to understand that. So we need to understand that the initial hypothesis that we take, it should be complex, but not too complex. So where do you draw the line is a bit of an art. So I think we as data scientists still have a job in that sense. So you got to think about it, right? So because theoretically what this graph is telling you is, if I have a model that is infinitely complex, I can achieve zero error on any problem in this world. That's essentially what this graph is telling you. Okay. Hopefully that makes a little bit of sense. Yeah, moving on. Other interesting developments, exactly. Thanks, Malini. It was a good segue into this. There are other meta-learning approaches now, including few-shot and single-shot learning. What these mean at a high level is fundamentally things like So can you do this with fewer and fewer examples? So prototypical learning. Can you actually have, and in NLP, we are using it a lot. In images, we still aren't, okay? In NLP now, GPT-3 is a model that you can use for multiple downstream activities, and it will perform very, very well with very few samples. So you can just prime it with a few sentences and it can do whatever. So that's an example of a very successful few shot learning type approach, right? Single shot learning is still, is out there. It's also valid. It's like, it's not probably gotten to the extent, or the success is not at the same rate as probably few shot learning. Single shot learning basically says that I will not give it any examples. Single shot or zero shot learning, where you're pretty much saying, it'll learn on its own. So that just means there should be some association between what you're seeing and what you're calling it. Anyway, I won't get into too much details of single shot and zero shot and few shot learning, but these are meta learning approaches that are getting traction now. Self-supervised learning, you must have heard about that AlphaGo and AlphaGo Zero and all of those games. Reinforcement learning. So self-supervised learning, the algorithm learns against itself. So once you prime it with some success rate, it keeps playing against itself. Keeps figuring out when it is making mistakes and keeps improving it. So essentially what you're saying is, this is a good statement that we make, right? Hearing, moving, and seeing cows tends to occur together. So if you know one, you can learn the other. So that's the self-supervision bit of it, okay? It's actually a very popular technique, and this is something that in the next 10 years, people who are young, people who are starting off in this will see a lot of this. Self-supervised learning is becoming mainstream now. Doesn't take away active learning though, because you still got to prime those, and active learning still has a role to play. But that paradigm is getting. The third one, I don't think I will get into too much. It is a very, very mathematical technique. So you can kind of, it's called kernelizing Hilbert spaces. So you can, that's another, because most neural networks are called over-parameterized, right? They're kind of over-parameterized. So because if you guys want to play with it, you can actually play with it. Let's say you take a VGG16 model and train it on an MNIST data set, okay? You probably have close to what, 2 million parameters trying to do that. Once the model is trained, try pruning off all these zero nodes in it, in the network. You will be left with hardly 8,000 nodes, and it will still give you the same accuracy. So the question is, if you could achieve that accuracy with 8,000 nodes, why did we do it with 2 million nodes? Commonsensical question, right? That's a question for another day. The next webinar, think about it. It's an interesting question, right? Why does that work? If that works, why do we still do this? Bottom line, yeah, very interesting space. A lot of opportunities to build the next theory, because as I said, the VC theory doesn't work anymore. So who knows? Maybe it will be named after one of you guys on this call. So we are waiting for the next theory for active learning in the deep learning era. We don't have it. Hopefully one of us will do this. Thank you guys. Thanks very much. Thanks for all the patience, and thanks for listening through.
Cool. Does anybody else have any other questions? Okay. Looks like it's time for some music, if that's what I'm hearing. Lalita, anything else that you want to talk through? Yeah, I know you said we'll meet in person. Hopefully, yes. Yeah, let's do this in person. There is a lot of catching up that happens post the session as well. But yeah, if anybody's got any other questions, if anybody wants to reach out, send some comments, feedback, etc., definitely welcome. You have Lalita's email address. You can write to her. You can scream at her too. She'll let us know all the good stuff.
Yeah, and she'll keep all the bad and ugly stuff with herself. Haha.
Yeah, yeah.
Thank you, guys. Thanks very much.
Thank you so
Appreciate it.
much.
Thank you.
Bye. Oh, it's my email at the end. Okay.
Yeah, if it's intelligent questions, they go to you. If it's good and bad feedback, it goes to Lalita.
Thank you. Thanks, guys.
Thanks, everybody. Bye-bye.
Thanks.
Bye.
Bye.
Amazing session. Thank you. Thank you.